Welcome everyone to the first week of Advanced Machine Learning. The goal of this week is to present some fundamentals, the mathematics of neural network implementation and the basics of PyTorch. I know that you are all from very varied backgrounds, so the aim for this week is that each of you take your understanding of neural network theory as far as you want to go. You will not be examined on it. However, at the very least, we do seek that you gain sufficient understanding of the constraints of forwards and backwards propagation, the building blocks of network optimization, to know how this impacts choice of loss function, optimizer, and architecture when motivating your own choices in building networks going forward. To achieve this, in the next lecture, I will take you through the mathematics of optimization for a single neuron classifier. As this is essentially logistic regression, it may cover some of the same ground of the machine learning course, and in that sense should hopefully be within reach. I ask that you all at least watch it, as it will give you intuition to understand how backpropagation works and the constraints it works under. The third lecture will cover multi-class classification, the softmax operation, one-hot encoding, and choice of activation functions. This is again core content, as you will use these components in future networks. The fourth lecture, however, will involve more advanced matrix algebra, and I leave it as optional content for those of you who want a deeper understanding of the mathematics and implementation practicalities of neural networks. It's highly recommended for those of you on the CDT to go through this and complete the tutorial associated with it. After that, we will get back onto the more accessible topic of the basics of PyTorch. PyTorch is a coding language for deep learning which is designed to be as close to Python and as easy to learn as possible. So hopefully this should be within everyone's comfort zone. We will start by first looking at the basic unit of neural networks, the artificial neuron. The basic biological unit of brain computation is a neuronal cell. Each cell is essentially an electrical device which receives signals at the dendrites which surround the cell body. The cell body performs the computation of the cell, deciding when to pass on the signal, and when it does, it transmits signals down the cell axon to the synaptic terminals, where it then connects with other cells. Artificial neurons are designed to represent a simple model of this biological process. The modulatory effect of the different synaptic connections is modelled through linear multiplication with input signals X, with weights W. If the final sum is high enough, modelled through a nonlinear activation function F, the artificial neuron is allowed to fire in response to that pattern of activation. Where the full linear term includes a bias, which shifts the centre of the prediction from 0. The idea with neural networks is that we will learn the weights and biases during training by changing them so as to minimise some cost function or loss. This will tune certain neurons to respond more or less strongly to different types of input. In this way, individual neurons can be viewed as simple classifiers. For example, if we use a sigmoid activation function, shown here as f, then what we are left with is logistic regression, where z equals 0 here defines the separating hyperplane. The bias term W0 has shifted this line from the origin, and all data points with z greater than 0 are assigned the positive class, and all data points with z less than 0 are assigned the negative class. The purpose of the sigmoid function is then to squash the result of the linear transform into the range 0 to 1. This can then be viewed as a probability of y hat, or the prediction, as being 1, such that the end result will be a prediction of y equals 1 if z is greater than 0, and 0 if z is less than 0. The activation can also be seen as a probability of the artificial neuron firing in response to an input. Fully connected neural networks, otherwise known as multi-layer perceptrons, then result from combining these simple classifiers together in a multi-layer network. This allows for the learning of complex nonlinear functions. For example, a simple two-layer neural network with one hidden layer and one output layer can optimally separate the following nonlinear distribution of classes represented by two concentric circles. Since each one of the neurons in the hidden layer can learn a different separating hyperplane, as shown here, these can be combined as follows to create one single nonlinear prediction, where this link at the bottom here takes you to the TensorFlow neural playground, where you can try this exact problem for yourself. So as shown in the example, we need 3 neurons in one hidden layer and only one hidden layer, where the output neuron is modelled separately. All we need to do then is press go on the training. And we see that it accurately learns the correct nonlinear boundary, returning a low test loss. Why not stop the video and have a go at the same problem? You can change the test train ratio or change the activation function or any of the other parameters. You might also want to change to some of these other classification problems. Note that without activation functions, there would be no point in learning multi-layer networks, as the network would just combine all linear transforms together into one single linear transform, remembering from our basic machine learning lectures that linear transforms are described by matrices and we can combine these into one matrix through multiplication. However, with the activation functions, the neural networks can become very powerful indeed. In fact, it can be shown that neural networks can predict any function you can think of. This leads to neural networks being described as universal approximators, where even a network with a single hidden layer can in principle hold this property. If you're interested why, there's a really nice tutorial on this online neural network book. While, however, this is theoretically true, it has been seen that wide networks, so ones with many neurons in each layer, have a tendency to memorize inputs and not generalize well. Further, training deep networks which create hierarchical descriptions of data can be particularly useful for problems such as image recognition and classification. So in summary, artificial neurons simulate biological neurons but in a crude way. Biological neural networks have much more flexibility over the signals they send, where action potentials of biological neurons are not continuous functions but rather single spikes in activity released as a result of an accumulation of potentials or spikes received from other neurons. These can be excitatory or inhibitory, increasing or decreasing the chance of firing. While biological neuron spiking can be seen as a binary process, artificial neurons apply continuous activation functions such as sigmoids. Doing so supports differentiation of the loss with respect to the parameters of the network, which we will look at in the next lecture. And so this has been fundamental to the development of optimization through backpropagation. So each artificial neuron may be seen as a simple learning model all of its own, but the power of neural networks comes from stacking these models together with many neurons in each layer, combining multiple layers. Multi-layer, fully connected neural networks of these types are often referred to as MLPs or multi-layer perceptrons. We will look at how to implement these from scratch over the next few lectures, but the real advances of deep neural networks for image processing came with the development of convolutional neural networks, which we will introduce next week.